Okay, let's start with the next topic in the greedy algorithms that we had started. So, we in the last class we did the Prim's algorithm. We started with a minimum spanning tree, and in order to find the minimum spanning tree in the graph, we studied about the Prim's algorithm. In the Prim's algorithm, we had discussed that first of all, the first step in the Prim's algorithm is that we choose the minimum edge, or you can say the edge with the minimum weight, and then we pick up all the edges which are consecutive or which are connected to these edges, and we are picking them up in such a way that all these edges, right, so they do, if there is an edge which forms a cycle, we will not be considering that edge, we will be discarding that particular edge, and we have to consider the edge with the minimum weight, because we are trying to find out the minimum spanning tree. So the minimum spanning tree is a tree which spans all the nodes in a graph, right, and with minimum weight. So, and another thing that is important is that the you can say we are trying to form a tree, so tree can't be cyclic. So if there is an edge which is having minimum weight, but if we will incorporate that particular edge and that may form a cycle, we will discard that particular edge, we will not be considering it, and then we will be considering some other edge which do not form the cycle. So another algorithm which is used for finding the minimum spanning tree is the Kruskal algorithm. So what is the difference between the Kruskal algorithm and the Prim's algorithm is, in the Prim's algorithm that we have been selecting all the edges consecutive to the edges, the first edge that has been selected, and then we are finding the connected edges. So the Prim's algorithm, it always forms only a single tree, one minimum spanning tree. But when we are working with the Kruskal algorithm, so in that case, Kruskal said that there is no need to find out the edges. You may not get a good spanning tree if we consider only the edges which are connected to the previously considered edges, right? Previously considered nodes. So what the Kruskal says, that you consider the complete graph, and one by one you pick up the edges which have the minimum weight. That means you sort all the edges in the decreasing order of their weight, and you keep on picking up all the edges one by one which have the minimum weights. So since you can just imagine, if we have a graph, and the in the graph we are picking up the edges which have minimum weight, so they may not be connected to each other. So you can say that in the Kruskal, when we are applying the Kruskal algorithm in order to find out the minimum spanning tree, so we have a forest. So in the forest, what we have multiple trees, and after that, see, you can say we start with the creation of the multiple trees, and then at some point we know that we will come across the edges which will be connecting these trees with each other. So we will be what we will be doing, we will be connecting the trees and in the forest, and finally we will be able to find out the minimum spanning tree. So how do we connect? So basically we are going to apply certain operations which are known as the union operations or union find operations, which help us in merging all the trees in the forest into a single tree that we will call as the minimum spanning tree. And the similarity between both algorithms is that we have to discard the edges which may form the cycle within this particular tree. So we have two options, because in the Kruskal algorithm we will be creating the multiple trees. So you have to find out if this is an edge within the same tree or between the trees. If it is between the trees, it will not form a cycle, but if it is within the tree, it is going to form the cycle. So here you see, this is the example on the left hand side. So we have a graph from A, B, C, D, E. So in this particular case, we have a particular edge A to D, which forms a cycle. Similarly, B to D, this is also forming a cycle, right? So we will be avoiding such kind of edges for consideration in the MST. So here we have seen that you see all the edges have the different weights, and the first step that we do when we apply the Kruskal algorithm is we sort the edges in the decreasing order of their weight. So here you can see we have considered all the edges in this particular table from the this is DC, AE, AD, ED, BC, AB, BD, and they have the weights 2, 3, 5, 7, 9, 10, 12. So we have arranged them in the decreasing order, increasing order of their weights. So the first task has been done by creating this particular table. So from here we can see that when we are considering if we create a minimum spanning tree from these edges, if we consider the first one to be DC and second one is AE, and here you can see DC and AE are not connected to each other in any of the ways. They have no common edge. So what is going to happen is we will when we start creating the minimum spanning tree, we will have one edge DC and another edge as AE. So next we move on to AD. So here you can see since AD has not been spanned yet, so we can create that edge. So we can create AE. It is already there. Then we can join the AD. So now next move on to ED. So ED here is, see, if we consider this edge ED, which is having 7 weight. So here you can clearly see that AE and AD, they are already connected, and joining this edge will form a loop. So we will be discarding this edge from here. We will not be joining this particular edge. So next we move on to BC. So when we move on to BC, so we can DC is already joined, but when we consider the BC, we can join this particular edge. We can consider it because it is not going to form any loop. So we can join this particular edge. Next we move on to AB. So AB is also not going to form any loop. So we can consider the AB also. So then we move on to another edge, that is BD. So the BD, if we will consider, that is going to form the loop, that is A, B and D. So we will be discarding this edge. So the tree formed by discarding few edges and by considering the edges. So here you can say we are able to find out the minimum spanning tree. So how do we start? So we have step A, that is that A is equal to the set of all the edges that we are going to consider, and F is equal to E is the set of all edges, right? A is a complete set, that is empty, that we will be considering. So it is going to form the minimum spanning tree. So we choose the edge E in F of minimum 8. So what we have done from this particular example, so in from the set of edges, we are choosing the edge DC with the minimum weight, and check whether adding E to A creates the cycle. As I said, when we were choosing this, we were checking whether if we will consider this particular edge, this is going to create a cycle or not. If yes, we will remove this edge E from the F, and if no, we will move edge E from F to A. So A is going to give us all the edges which are going to create the minimum spanning tree. So if F is equal to empty, that means because A is the set of all the edges with the minimum weight. If it is empty, that means no more edges left to be spanned. All the nodes have been spanned. So we say that we can output the minimum spanning tree with the nodes and the edges. Otherwise, we will keep on repeating all the steps. So when we are implementing, see, when during the implementation, some important questions that we come across is, how does the algorithm choose edge E out of the F with minimum weight? So as we have seen, when we have to do this particular task, so what we have done, we have sorted all the edges in the increasing order of the weight, and then we walk through the edges in this particular order. So we will be considering each edge one by one, and if it is causes a cycle, we will be throwing it away. We will not be considering that particular edge. Then how does the algorithm check whether adding E to A creates a cycle? See, we said that for sorting, we know we can sort all the nodes according we have sorted all the edges as per their weights in the decreasing order of their weights, right? Now how to check whether it creates a cycle or not? So for checking this particular, you can say for checking whether this particular edge will create a cycle or not, what do? We, at each step of the algorithm, we have A, which is acyclic, so it is a forest. So if you and we are in the same tree, then adding edge to A will create a cycle, as I said earlier also. If, because we are creating, when we are applying the Kruskal algorithm, we are not forming one spanning tree in the beginning. In the beginning, we say that we will be creating the multiple spanning trees, because we will be choosing the edges randomly based on their minimum weight. So if in that case, if you and we, both the nodes are in the same tree, so then adding the edge may create a cycle. But when both are in the different trees, so they may not create a cycle. Then how to test whether you and we are in the same? See, first we created the logic that how to find out whether it will create a cycle. So we said that if it is in the same tree, it will create a cycle. If it is not in the same tree, then it will not create a cycle. Then how? Yes, yes, bacha. Somebody was asking something. I hope I am audible. Amisha,
Yes, ma'am.
Amisha. Okay. Right. So then the question arises is how to test whether you and we are in the same tree or not. So finding that, to find out the answer for that, what we have is we have one operation that is called as the find set. So using the find set, we try to find out whether that particular set, whether that this particular edge that exists in the same tree or a different tree. And for the from the implementation perspective, see, as I said, over the period of time, we will be joining these trees, and this will happen as we come across some edges which are joining the two trees. So in that case, what we have a special data structure that is known as the union find data structure. So this union find data structures that helps it helps us in joining the multiple trees which are there in this particular forest, in order to finally get a single tree that is a minimum spanning tree. So for performing this kind of implementation, so what we have to use a disjoint set data structure vertices in a tree. So so that we can find out that if find set u is equal to find set v, that means both are same or not. Depending upon the answer, if they are not in the same tree, accordingly we will consider that particular edge. If they are in the different they are in the same tree, we will not be considering that edge. So in the union finds you can say this particular data structure, it supports different functions like create set. So this create set takes just unit time, because we have to just create a single element, right, u. Then we say find set u. So find set u, we have to find the set containing the element u, right? So using this, what we can do is, so we can find the set which is required in order to find out whether this particular node, it belongs to the same tree or to a different tree. Then the union operation. This union operation is going to help us in merging the two trees in the forest. So whenever there is an edge which joins the two trees, so first of all we say whether it belongs to the same tree or not. So if they are in these two this particular edge, you can say joins the nodes of the different trees, so we will be considering this particular edge, and then we will be combining them. We need to merge the trees so that we are able to create one subtree of that particular graph, so which will have all the edges of the two trees in the forest. So similarly, we keep on creating executing this union function between you and we at every step wherever we come across such kind of edges, and finally we are able to get the single minimum spanning tree. So here you see, we what do as we have seen in the example. So sort E in the increasing order of their weight. So this we have seen. This is the first step in the algorithm that you see. We have sorted all the edges in in the increasing order of their weight. And this particular sorting operation, this takes E log each time. So E is the number of edges which are there. You can write E is equal to N if N is the number of edges. Then we have A, that is empty set, which stores all the edges for forming the minimum spanning tree one by one. Then for each U and V, for each vertex in the complete vertex, what do? We create a set of U. So we are creating the set of U vertices. Then for each edge, that means you each edge which is between the two vertices ui and vi, let's say it is u1 v1 u2 v2 u3 v3, like that. So from 1 to e, that is for all the edges, number of edges is equal to number of vertices minus 1. So if find set u is not equal to find set v, so here you can see, if both the sets are not equal, that means if they don't belong to the same tree. So if they don't belong to same tree, only then we will be adding this h ui vi to a, and then we will be forming the union operation of both the your edges, right? So that when we perform the union operation, you can say these trees are combined together. So multiple trees, they are combined together to form the minimum spanning tree. So with the proper implementation, when we are using the union find operation, so here you can see that the Kruskal algorithm has a running time of E log of A. So here you can see this is a proof of why Kruskal algorithm is correct and why it is help us in providing the better solutions as compared to the Prim's algorithm. So if we consider an edge AZ which has been selected by Kruskal algorithm, and UV be the edge to be added next, it suffices to show that there is a cut with respect to which respects A and UV is the light edge crossing that out. So it keeps a track of this particular thing, and it helps us to find out that this particular edge which is going to be added in the minimum spanning tree, so that is basically going to respect this particular edge, and it is going to be the lightest one, that means the edge with the minimum weight. So let A dash and B dash and E dash denote the tree of the forest A that contains U. So if we consider the cut V dash and V minus B dash, then we observe that there is no edge in A that crosses this particular cut. So the cut respects this A, and if the cut respects this A, that means we will not be able, won't be any kind of cycles that will be created over there. So that means this particular creation of the minimum spanning tree and the elimination of the cycles, that is taken care of completely by the Kruskal algorithm, and we are able to get the best solutions using the Kruskal algorithm, that means the minimum spanning tree using the Kruskal algorithms. Then next we have another category of algorithms which are used for finding the shortest paths. So this is another graph algorithm which is which we use for solving the real world problems, like finding the shortest route from one place to another place. So in this particular category, we may have different types of problems. Like we study about the traveling salesman problem. So traveling salesman problem, one aspect we were discussing over there is backtracking algorithms. So whenever we are not able to reach to the solution, that means if there is no path along this particular direction, in the direction we are moving, so in that case we have to backtrack. So another problem, another perspective to that is, see, in the your traveling salesman problem also, we try to find out the shortest path. So when we are finding the shortest path, that means it is a minimization problem. So we are trying to minimize the path so as much as possible. If it is a minimization problem, then we say it is an optimization problem, because in the optimization algorithm, we either try to maximize the profits or maximize something else, right? Either our goal is to maximize, or our goal or objective is to minimize. So when we have our goal is some sort of minimization or some maximization, then we are talking about optimization problems. And then for solving the optimization problems, we use the greedy algorithms. So there is another greedy algorithm which we are going to study, that is a single source shortest path algorithm. This algorithm is having the multiple variants also. So as we change these values, so these variants have a different complexity. So let us say we have a problem to find out the shortest path where the source and the destination are fixed. So in that case, once the source as well as the destination are fixed, then we have to find out the shortest path from the source S to D. So another variant that we can have is a single source shortest path problem. So that means our source is fixed but destination is not fixed. So if we have multiple destinations, in that case we are trying to find out the shortest path to each of the destinations T. So here today we are going to study about this particular second variant of the shortest path problem. Then another is the all pair shortest path problem. So here you can see if we have all pair shortest path problem, what is the complexity of that this particular algorithm and how difficult it would be. That means let us say if we have 5 cities and from every city we want to find out the shortest path to every city. So every city is a source as well as the destination. So from one city you want to find out what is the shortest path to all the other cities. So you can say you can understand what is the complexity of this particular task. So let us study for the first one variant of the shortest path algorithm, that is single source shortest path algorithm. And the algorithm that we use for solving this kind of problem is the Dijkastra algorithm. So let us say we define the shortest path properties first. So this the distance between u and v to be the weight of the shortest path from u to v. See, when we are trying to find out the shortest path, so it may be, so we must have some weight. This weight may be representing anything. It may be time, it may be distance, or it may be some relationship. So we are given some weight between the two edges. Only on the basis of that particular weight we specify that we are considering that particular weight and we are trying to find out the shortest path. So let us say in this particular problem the weight represents the distance between the source and the destination. So the shortest path satisfies the triangle property inequality. So that says that the distance of u and v is always less than the distance of ux. Here you can say the distance between u and v. Here you can say we have 3 points which are connected. So the u, v and x. So here you can say the distance between u to x is always less than equal to distance of ux to plus the weight of x and v. So that means this distance will always be less than this. So this triangle inequality, this help us in finding out the updated weight for the next vertex. So using this, see this technique is used for we can say updating the values of the distance. See if the new distance is, let us say, less than the previous one, so we will update because we have to find out the shortest path. So here you in this particular, in these algorithms, this updation of the distance, that we are saying distance of u to v. So there is one direct path and there is one indirect path. So we are talking about if we are this path is no longer than any other path, right? So you can say if we are computing the distance from u to x and x to v, so we have first considered the distance between u to x, that was also weight, but now it is the distance of the x, we are calling it as delta ux. So when then from x to v there is some weight which is also a distance. So we say that this is, if this distance, this direct distance from u to v is less than this equal to delta ux plus w xv, then we will what we will do, we will update the value of the v. So the v will be having a new value. So here you can say this relax operation and say the idea for all v maintain upper bound dv on delta sv. So that means in the beginning we always give the upper value and then we will keep on reducing that particular value. So this process of updating the values of v, or you can say in the process we are trying to reduce the values of the v any vertex, right? So that is called as relaxation in shortest path algorithms. So what do we do in the relaxation? We check if dv, that is the distance of v, is greater than the distance of u plus w, then update the value of dv, that is dv is equal to du plus w. We will do this with the help of example. So let us say this is Dijkastra algorithm is one of the shortest path finding algorithm. So using the Dijkastra algorithm, we are trying to solve the problem of single source problem. So single source, multiple destination, this is the, you can say, the second one, single source shortest path problem. Given S, for each D, find the shortest path from S to D. So using the Dijkastra algorithm, we will try to find out this particular distances. So let's say what we do initially. So this is the graph that we are given, and in this particular graph, we have the edge weights which are given, and this is a directed graph. So in this particular graph, we can see that we have multiple edges which are connected to each other. But here we see, because it is a single source shortest path problem, so we are already specified that S is the source. So we have to find out the minimum distance of S to U, S to V, S to X, and S to Y. So all the destinations. So what we have to do? So initially, what do? We assign all the values as infinity, the maximum values, the upper bounds, as I said. In the previous step, we said the idea is for all we maintain upper bound distance dV on delta SV. So what we are doing, we are maintaining the upper bound. So initially we have assigned the maximum value to all the vertices, that is infinity. So for each in the pseudocode also you can see, for each V, for each vertex belonging to the complete set of vertices, dV is equal to infinity. So after that, what do? So from here we see what are the directly connected vertices from S. From S to S is directly connected to U, S is directly connected to X. So what do? So once this is directly connected to S, and the weights of S to U is 10 and S to X is 5. So what do? We assign these values to these connected vertices. But and we are moving from S to other direction. So we are looking at the directed edges. See, we have an edge from S to Y, but it is in the opposite direction. That means there is a route from Y to S, but not from S to Y. So these highlighted red edges, these are the directed edges from S to, so we have a path from S to U and S to X. So initially their values were infinity, but these edge weights, the values of the distances, 10 is less than infinity, so we have replaced the infinity with 10. 5 is also less than infinity, we have replaced this with 5. So from here we see, since there is no edge directly from S to V and S to Y, but we can see that again U and X are also connected to the other edges. So we do the relaxation process. What do? See, from here you have seen we are trying to find out the minima using the extract mean. So using the extract mean, we say from S to X is 5, that is minimum as compared to that of U. So from here you see that what are the other edges which are connected to X. From X we have a edge to U, then another edge to V, and another edge to Y. So from here you see, since 5 to X to Y is infinity, and if we see the weight, so the initial value of Y is dV over here, and here you see d of X plus the edge weight. So this is 5 plus 2, 7, which is less than infinity. So what do? We can relax this Y vortex. Similarly, we can relax this V vortex, because 5 plus 9 is 14, which is less than infinity. So here you see, and another, here you can see, sorry. And since 5x was also connected to U, and if we see 5 plus from X, see, we are going from S to X to U, and you see 5 plus 3 is 8, which is less than 10, and this edge is connected to X. So we are trying to relax all the edges which are connected to the minimum, the vertex which is having the minimum value. So here you can see this particular condition. If V is a subset of all the vertices which are adjacent to the current minimum vertex. So the current minimum vertex was 5, and we are looking at the adjacent edges which are connected to X. So the currently selected vertex, we are finding out the connected one, the adjacent one. And if dV is greater than du plus w, so we are updating this. So we are applying. So when we are replacing the infinity with the minimum edge weight which is connected to this particular edge. So we are doing the relaxation step. So similarly, if we see, although 10 was already u vertex was already relaxed, but still it can be relaxed. See, basically Dijkastra says if some edge is already relaxed, you need not relax it further. But here you can see, if we can minimize this value further, this can be further relaxed. So, and it is adjacent to this, we are relaxing that. So we have 5 plus 3 is 8, which is less than 10. So we relax this node also. So here you can see this is the updated values. So the two nodes are relaxed. You can say your U, V, and why? So here you can see the blue color is indicating that all two of these nodes have been considered and they have been selected, and now we are moving towards the next step. So from 5 we have to see which of the particular vertex is having the minimum value. So here you can say one is 8, another is 14, and another is 7. So 7 is having the minimum value, so we select this particular vertex. So that's why its color is changed to green. So from here you see, so we have two edges, two vertices which are connected. So one is S and another is V. So the distance that we see from here is, see, if we see the distance of Y to V, it is 7 plus 6, 13, which is less than 14. So we can relax this particular vertex. Right. So now we see, so the next selected vertex we have, we can see over here is between 8 and 13, that is 8. So here you can see we are selecting the extract min. So U is equal to extract min, the vertex which is having the minimum value. So you can see how many times we are going to call the extract min. So this particular function is being called to find out the vertex with the minimum value. So now here you see what are the vertices which are connected to U, which is having the 8. So here you see U is connected to 5, which is having the value of 5, which is less than 8, because the new value it will get is 10. It is already relaxed, it is having a minimum value. So another vertex which is connected to U is connected to is V. So here you see the new value it will get is 9 and the old value is 13. So we can further relax this particular vertex. So its updated value is 9. So now we see this particular vertex. This all the other vertices are already relaxed, and the new vertex that we get over here is, so the only vertex which is connected to V is Y. So if we try to relax this Y, we see it will get a new value of 13. 9 plus 4 is 13, and its existing value is 7. So it is no, we need not apply that relaxation over here, because this condition is not satisfied. That is, if D of V is greater than this. Since D of V is less than this, so this particular relaxation will not be applied. So these are the final values of, you can say, the source to all the destinations. So source was S. So here you can see from S to X, the minimum value is 5. From X to Y, the value is 7. From S to U, value is 8. And from S to V, the value is 9. So that means if we want to go to any of these destinations from the single source, the minimum distance you have to cover is, let's say it is 5 kilometers, 7 kilometers, 9 or 8, and you will be able to reach to that particular destination. So this is how we apply the Dijkastra algorithm for finding out the shortest path from a single source to any of the destinations. So if you have any queries regarding this, so you can ask. So then we have seen how many times is the extract min called. Extract min is called as, you can say, equivalent to the number of vertices that we have. Then how many times is the decrease key called. So decrease key is, you can say, at max how many times it will be called. So you understand. So can you tell me which particular algorithm we will be used for implementing the such kind of task? So where do we use the decrease key? We can use the heap data structure over there. So what will be the total running time? So the total running time is O V plus E log of V using the binary heap for Q, and we can achieve O V log V plus E using the Fibonacci heap. So you can use the different data structures for solving the same problem. Here you can see the complexity that we are able to achieve using these two data structures when we apply the Dijkastra algorithm. And then can you anybody tell me what happens if G has negative edges? Any idea? Yes? Yes, anybody can tell me what will happen if the negative edges? See,
I
it's
mean,
the Dijkastra
we,
algorithm. See, when the Dijkastra is a scientist who gave this particular algorithm, and when he gave this particular algorithm for finding out the shortest paths, so he did not test this algorithm for the negative values. So later on, some other scientists were trying to solve their problems using this Dijkastra algorithm, they found that this Dijkastra algorithm may be suitable. So is also suitable for the negative values which are assigned over there. So you can say that Dijkastra algorithm is suitable for finding the you can say finding out the shortest values even with the negative weights. So but Dijkastra had not when Dijkastra developed the algorithm, he hadn't tested whether it will be suitable or not. He gave this algorithm for the positive values only. But when you see that when we use the negative values also, so we are able to find out the shortest path. So Dijkastra algorithm, using the Dijkastra algorithms, even if you are given the negative values, you can find out the shortest path. So that's it for today.